Hello, in this video I will explain the three stages of liquid quenching. As I have explained before, the goal of quenching is to cool steel from austenizing temperature quickly enough to form martensite. But before I proceed with the explanation, I would like to show you this video clip here showing how liquid quenching was performed. Quenching is metals heat treatment that was performed in order to alter the microstructure of steel, often from austenite to martensite. As we know, microstructure of steel is what determines its hardenability and strength and also its toughness. So before quenching can be done, the steel must first be heated to alter its microstructure back to austenite. After soaking it at an elevated temperature for a period of time, the complete austenite will be developed in the microstructure and it will be removed from that elevated temperature. So during liquid quenching, the temperature of this metal must be rapidly cooled, and this can be done by dropping it into a liquid in order to transform its microstructure from austenite to martensite. So you will see in a few seconds that quenching process will be performed to this steel. When a hot component comes in contact with liquid quenching or liquid medium, there are normally three stages of quenching. The three stages of quenching are vapor stage, boiling stage, and convection stage. So here is what happened during those three stages. This is a typical cooling curve during quenching. Immediately after the start of the quenching coolant or the quenching medium will get vaporized due to metal being at high temperature, and a continuous vapor blanket will envelop the surface of the object. Now, no liquid can come in contact with the metal surface, and heat escapes from the hot surface very slowly at this stage by radiation and conduction through the layer of water vapor through liquid vapor interface. Since vapor film are poor in heat conductor, the cooling rate is relatively slow at this stage. Ideally, the vapor phase will be as short as possible to come up with steel with high hardenability. During this stage, the vapor blanket is broken intermittently, allowing the coolant to come in contact with the hot surface at one instant, but soon being pushed away by violent boiling action of the vapor bubble. The bubbles are carried away by convection current and the liquid touches the metal again. Heat is removed very rapidly at this stage as the heat of vaporization, as indicated by the steep slope of the cooling curve. The rapid cooling in this stage soon will bring the surface below boiling point of the quenching medium. The vaporization will then cease. Steel in the austenitic condition transform most rapidly at this stage. The convection stage begins when the temperature of the surface of the object decreases to boiling point or below boiling point of the quenching medium, and this will prevent any more formation of vapor. The cooling is due to convection and conduction through the liquid. The cooling rate is at the lowest at this stage. I will now show you the still images sequencing the mechanism of quenching. The moment the heated object immersed in the liquid, a vapor film can be seen forming around the object. After 5 seconds, boiling starts at the corner of the object. And then after 10 seconds, the boiling front moves along the object. After 15 seconds, all three faces can be seen. Some part of the object starts to cool down. After 30 seconds, the part is nearly the end of the convection phase. And after a minute, the convection phase ended. It can be observed that the three phases of quenching can occur simultaneously on the part. As I have mentioned previously in the lecture video, there are three mediums of quenching in heat treatment of steels, and these are brine, water, and oil. Quenching in salt water or salt solution often will result with steel with the highest hardenability. Why? The addition of salt will assist in breaking up the vapor blanket, and therefore the coolant or the quenching medium will become in contact with the hot surface of the metal quicker. During quenching, crystals of salt were deposited on the surface of the steel. The localized high temperature will cause this crystal to fragment violently, and this will create turbulence, which will destroy the vapor film, and this will give the highest maximum cooling rates. This means that a lot more austenite will be transformed to martensite, which is hard in nature comparing to ferrite and perlite microstructure. On the other hand, why is quenching in oil exhibit the slowest cooling rate between the three medium? The quenching velocity of oil is much lesser than water. This is mainly because the thermal conductivity of water is higher than the thermal conductivity of most oil, and this will result in faster removal of heat from the hot material if it's quenched in water. And this is why water has a better quenching efficiency. The faster the cooling, the greater the suppression of diffusions of carbon in the crystal lattice, and therefore more martensite transformation will happen. Subsequently, it will improve the hardness or the hardenability of steel. Before I end this video, I would like to emphasize that there is no perfect method on the selection of quenching medium. Each of the medium has its own merit, and depending on the steel alloy that you want to heat treat and the resulting mechanical properties that you want, the choice of quenching medium often involves experience. Thank you for listening. Have a good day.